So it's my pleasure to introduce Mario Velasquez. Many years ago was my PhD student, and he's a professor now at the National University in Bogotá, Colombia. So he'll tell us about on the group of homology and KP of the semidirect product with source.
For the invitation, the organizers. Okay, the idea is to talk about how to compute the group cohomology and the K-theory of the reduced C-star algebra of these kind of groups with M free of squares. Okay, let me give definitions. Let rho be a homomorphism between Z where M to this general linear group. Rho induce a group structure on this Cartesian product given just by this equation. B plus rho T times W, and in the second component Ts. Okay, we denote this group by Zn semi product rho with Z M, or simply Z to the N semi product with Z over N. And for this talk, I will suppose that M is free of squares. Okay. Okay, the goal of this talk is give a method to compute the group cohomology, the cohomology of the classifying space of this group with integer coefficients, and the K-theory of the reduced C-star algebra of the group. Okay, an outline of the talk. First, I will recall some definitions about classifying spaces. Later, some definition about group cohomology, group extension, and the Lyndon-Hoschild-Serre spectral sequence. Two properties that will be crucial in our computation: the property M and NM property, some previous results, constant isotropy modules, and how to compute invariance. Later, I will talk about the K-theory of the reduced C-star algebra, the Baum-Connes conjecture, again invariance, and finally some questions about the mainly about the K-theory of the reduced C-star algebra of this group for general N. Okay, classifying spaces. Let gamma be a discrete group. A model for the classifying space E gamma is a gamma-free, gamma CW complex that is weakly contracted. A theorem says that two models for E gamma are gamma homotopy equivalents. Another theorem, this map from E gamma to the orbit space, B gamma, is the universal gamma principal one. The examples, the classifying space for the integers numbers can be taken as the real numbers with the translation action, and the quotient is the circle. The classifying space for these cyclic groups can be taken as a co-limit of odd dimension spheres with the action given by multiplication by a primitive unity root of unity. Okay, for this talk, I need also talk about the classifying space for families. Here we work with families of subgroups closed under taking subgroups and conjugation. Let F be a family of subgroups of a discrete group gamma. A model for the classifying space of gamma respect to the family F is a gamma CW complex, EF gamma, such that satisfies these two properties. The first one is that every isotropy group of this space is in the family. And the second one is that for every element in the family, the fixed point set by this group is weakly contractible. Okay. It implies also that this space EF gamma is the universal space with isotropies in F. It means that every gamma CW complex with isotropies in F has a unique map up to gamma homotopy to this EF gamma. Some examples: when F is the trivial family, then the classifying space for F is just the usual classifying space. And when F is the family of finite subgroups, this E fine gamma is denoted by E bar gamma, and is called the classifying space for proper action. For gamma, our groups that to the n similar product with Z over M, the classifying space E bar gamma can be taken as R to the n with the action induced by the matrix rho. It is because this space is contractible, but also has finite isotropy groups, and the fixed point set of a finite subgroup is a linear subspace of R to the n that is contractible, and also is also a gamma CW complex. In general, it's not easy to construct models for E bar gamma, but if you consider the following assumption on gamma, it's possible to construct good models for E bar gamma. The assumptions are: the first one is the M property. It says that every finite group of gamma is contained in a unique maximal finite sum. And the second one is the NM property. It says that any maximal finite subgroup of gamma has a normalizer equal to itself. The first one property, think about, if you consider the poset of finite subgroups, things like that in the poset cannot happen. Okay? It is forbidden if the M property is satisfied. Okay, some examples of groups satisfying these two properties, M and NM. The first one is extensions with kernel pre-abelian and quotient finite, such that the conjugation action, this group over C to the n minus 0 is free. This example will be the main example for this talk. Another two examples, one relator groups, and this projective special linear group over the integer numbers. It is true because this group is an amalgam. Okay. For groups satisfying these two properties, M and NM, there is a nice model for E bar gamma. Nice model in terms of CW decomposition. Could be an explicit gamma CW composition, starting with a gamma CW composition of E gamma. What is the idea? The idea is that you could take MI via a set of via representative of the set of conjugacy classes of maximal finite subgroups of MI. Then we have an inclusion of gamma CW complex. It is because from this union of these induction spaces to E gamma, the idea is because we can construct a model of E gamma in terms of or attaching free cells to this union. We have this inclusion, and we can also contract EMI to a point, then we have a map to this quotient, to this orbit, gamma over MI. And then consider the gamma push out, this gamma push out. The theorem, to it by Davis and Luke, says that X is a model for E bar gamma. The proof is not so difficult. The idea is that X is a gamma CW complex with finite isotropy groups. And we have to prove that for every finite group, the fixed point set is contractible. Two cases. The first case is that H is a non-trivial finite subgroup. Then by M condition, H is conjugated to a subgroup of a unique maximum in I0. Then we have that the H fixed point of this union is just the fixed point of only one orbit. And moreover, the NM condition implies that the fixed point of this orbit is just a point. Okay. If H is the trivial group, the map pi is a homotopy equivalent because this space is contractible, EMI. And because this map is a co-vibration, then we could consider a homotopy inverse of this map and transfer to construct a homotopy inverse of this map. Then we have that X is contractible. Then X is a model for E bar gamma. It's a model constructed from a model of E gamma. Okay, let me talk a little bit about group cohomology. Let gamma be a discrete group. A gamma module M is just a module over this group ring. A projective resolution of a gamma module M is an exact sequence of gamma modules, where each pi is projective. This is denoted by P star maps to M. Just an example. Let gamma be this cyclic group with one generator T, and set with considered as a gamma module with the trivial action of gamma. Then this maps, or this sequence of maps, is a projective resolution. One observation: projective resolutions exist for any gamma module M. And then if you have a projective resolution and M be a gamma module, you can consider the cochain complex given by applying the Hom functor to the resolution P star. Then we get a cochain complex. The cohomology of this cochain complex is called the cohomology with coefficient in N. Okay. The theorem, one theorem is that the group cohomology does not depend on the resolution P star. One example: for gamma equal to Z over M, we have the resolution, and we apply the Hom functor to this resolution. We get this cochain complex M. The maps to M via multiplication by P minus 1, then later by this norm map, and so on. And we get this result. The group cohomology of this fine cyclic group with coefficients in M is just the fixed point module if I is equal to 0, and these two quotients, if is odd or is even. The kernel of the norm map module the image of t minus 1, t minus the identity, and the fixed point set, fixed point module image of the norm map. In fact, we have also that the zero group cohomology is just the module of or the group of gamma invariants for every discrete group, and in positive degrees, the group cohomology is annihilated by the order of gamma if gamma is finite. It means that in positive degrees, the group cohomology of finite groups is torsion. And a final observation about this, the group cohomology with integer coefficients is isomorphic to the cohomology of the singular cohomology of the classifying space P gamma with integer coefficients. Okay. So let's continue. For more complicated groups, it's not so easy to compute the group cohomology. One way to try to obtain these computations is using spectral sequence. So let 0 to A to gamma to Q to 0 be an extension, and let M be a gamma module. It is possible via spectral sequence to compute the group cohomology of gamma in terms of the group cohomology of the kernel and the quotient. It is the Lyndon-Hoschild-Serre spectral sequence. There is a spectral sequence with second page given by the group cohomology of Q with coefficients in the group cohomology of A with coefficients in M. And this spectral sequence converges to the group cohomology of gamma with coefficient in M. It means that you could give a differential over this second page and compute the cohomology of this cochain complex, obtain another page, and then you could do again the same game. Again, have a cochain complex and take the cohomology and so on. And in the limit, we recover a filtration of these cohomology groups. If you could solve the extension problem, you could recover the group cohomology. That is the idea.
Do you require A to be abelian?
Yes, in this talk, A will be abelian. But in general, it could be any. Here we are considering this cohomology group as a Q module via the conjugation action of Q over A. We say that the Lyndon-Hoschild-Serre spectral sequence collapses strongly if there are no differential, more differential in the second and in the other pages, and there are no extension problems. It implies that the group cohomology is just this direct sum. Direct sum of cohomology of Q with coefficients in the cohomology of A with coefficients in M. Okay? Okay. So what happened with our groups? The 2D semidirect product with Z over M. We could consider the following extension, the natural extension, with kernel, the torsion free part, and the quotient given by the finite group, Z over M. In this case, the Lyndon-Hoschild-Serre spectral sequence has this second page, the group cohomology of Z over M with coefficient in this cohomology group of the integer numbers. And we already know how to compute that. Where this cohomology group is naturally a Z over M module with an action induced by the conjugation action. in the case of these groups and this extension, we have the following result of Adem-Gomez-Pan and Petrosyan. If M is free of squares, the above spectral sequence collapses strongly, and then we have this isomorphism. The group cohomology of these groups are isomorphic to this direct sum of the group cohomology of cyclic group, with coefficients in the group cohomology of the integer numbers with the action. Here we have a non-trivial action of Z over M where this cohomology via the matrix group. Okay. Another theorem of Langer and Luke. If the conjugacy action of Z over M on this Zn minus 0 is free, then we have that the group satisfies the properties M and NM. In this case, also the Lyndon-Hoschild-Serre spectral sequence collapses strongly, and then again we have this isomorphism. Okay. These theorems allow to get some explicit computation by Alejandro Adem, Tuman, and Manuel. They compute completely the group cohomology when this number M is a prime number. And Langer and Luke compute at most completely the group cohomology in this case. The conjugacy action of Z over M is free outside the origin. Okay. Let me describe the computation obtained by Davis and Luke under the following conditions. The number M is a prime, and the conjugacy action is free outside the origin. The first theorem, the following. Let P, this capital T, be the set of conjugacy classes of subgroups of order P in the group, in this semidirect product. There is a bijection between the set of conjugacy classes of group of maximal subgroup in this case, and the first cohomology group of Zp with coefficient in Z to the n, and also is isomorphic to Zp to K. Blah blah blah, and K is really is n over P minus 1. Okay. How to prove that? It's not very difficult to prove that. Recall that the first cohomology group is the kernel of the norm map module, the image of T minus the identity. T is one fixed generator of Zp. Note that if we take an element in the image of the norm map and act by T, it is fixed by T. And because the action is free outside the origin, then we have that the norm map applied to gamma is 0. It means that the norm map is 0. Then this kernel is all the group, all set n. Then we have that the first cohomology group is just the kernel, the map, P minus identity. On the other hand, note that if we have a group of order P, it has a unique generator of this form, gamma, and the second component, the fixed generator of Zp. Then we have a map between the group Z to the n to the family of subgroups of order P in this group, just by taking gamma to the group generated by this pair gamma T. It implies also that the co-kernel of T minus the identity is isomorphic to this capital T. Finally, as the conjugation action on this set is free, the orbit of any element generate a subgroup of rank P minus 1. just take T, gamma, T applied to gamma, T square applied to gamma, and then so on. It has to generate a group of rank P-1. It means that this number P-1 have to divide to n. And moreover, every orbit generate a copy of ZP. It could be proved by hand, just by hand. They can generate a set of generators of Z to the n, and then you could modify the generators in the co-kernel to get exactly one copy of ZP. Okay, then proves that the first cohomology group is ZP to decay and also is in bijection with the Z capital. Okay, second theorem. This is a theorem of Davis and Luke. Suppose that again that the conjugation action of ZP on this set is free. Then the map induced by restrictions to the various subgroups is this map goes from the cohomology of the group to the ZP invariant part of the cohomology of the torsion-free part. Direct sum with these cohomology groups. That is the cohomology of the representative of the conjugacy classes of maximal finite subgroups. This map is injective, and for beta greater than n is bijective. Moreover, note that this part is a torsion, then the rank of this group is just the rank of the cohomology of the invariant part of, the ZP invariant part of the group cohomology, the group cohomology of Zn. And the torsion part is this direct sum of cohomologies. The torsion part on index beta is isomorphic to this direct sum, where this set is just the set of tuples in ZP to decay, such that we can represent each element, each classes with an element between 0 and P-1, and the sum is less than beta. Okay. Okay. The idea of the proof, just the idea, is that we have a G push out because the group satisfies M and N property. Then we have this push out. You could take orbits to this push out and get this push out. The orbits here give a point. Here we have a PP, P gamma, and here we have this quotient. We will denote this quotient by P bar gamma. But we know that that R to the n with the natural action is a model of E bar gamma. It implies that when you take the Mayer-Vietoris exact sequence corresponding to this push out, we have the following, this long exact sequence. But for example, as this B bar gamma is a CW complex of dimension n, for beta greater than n, this is 0 and this is 0, then we have homomorphism. This, for example, implies that for beta greater than n is bijective. The result of the result has to be obtained analyzing the long exact sequence together with the isomorphism given by the spectral sequence. Okay. So now I will describe how to compute the group cohomology in the general case with no assumptions on the conjugacy action, in the case where M is free of squares. Okay. What is the idea? The idea is that we take M, decompose it as a product of distinct primes. Let us fix one prime number and consider the following group extension. here I have to say that the first idea to compute this the group cohomology of these groups is try to use this result. We know that the group cohomology is isomorphic to this direct sum. Then you try to compute this explicitly, but it is very difficult to compute. I tried to compute many times, try to compute this group cohomology, and it's very difficult. Then the right idea to get this computation is the following. Consider another extension. What extension? Consider this extension. With kernel set n, we are product with set p, and the quotient. Sorry, here something is wrong. Yes, something is wrong. Here. Extension is this is the extension. Okay. This is the right extension. Okay. Forget this set to the end. Okay. Consider this extension and consider the following ring. That is the ring obtained by invert all primes different to p. And let us denote the cohomology, the group cohomology with these coefficients just by h sub p. Okay? Considering this extension, the right one, we have the following. You can consider the Lyndon-Hoschild-Serre spectral sequence. And the second page is given by the group cohomology of G with coefficient in the group cohomology of Z to the N semidirect product with ZP with these coefficients. And we know that for cohomology, it is a cohomology of a finite group. Then for positive indices, for positive degrees, does not contain p torsion. But because the coefficients, this cohomology only contains p torsion. Then we have that the second page of the Lyndon-Hoschild-Serre spectral sequence is concentrated at degree 0 because that. And then we don't have differential, we don't have extension problem. Then we have that the Lyndon-Hoschild-Serre spectral sequence for this extension with these special coefficients collapse strongly. And we also know that this zero cohomology group is just the invariance of the module. The module that in this case is the cohomology of the group, but with the ZP function. Okay. Then we have this theorem, reduction to invariance, the group cohomology with integer coefficients also, and the fixed point, the G fixed point of the group cohomology with ZP with the action or the group cohomology of this semidirect product have isomorphic p torsion parts. Okay. Okay. Then the strategy to compute these cohomology groups is use the Wolfgang Davis and Luke results. to get computations, to have an explicit description of this cohomology group, and try to compute G invariants. Okay, that is the idea. Then we have to compute invariants. How to compute the invariants? Okay. Note that for any action of set P over this group, over set to the n, we can take the invariant part, set P invariant part, and a complement. We can decompose set n as the invariant part and direct sum with a complement. Okay. We can then, in this case, because the action of the group set P is trivial over the invariant part, then we could decompose this group as a Cartesian product. And then you can apply the Q-net formula, and because the coefficients, sorry, not for the coefficient, because this part has a free cohomology, then the Q-net formula really gives an isomorphism between graded groups. Then we have that the cohomology of this group with these coefficients is isomorphic to the cohomology of the invariant part tensor with the cohomology of this semidirect product. But the important property is that because this M doesn't have invariance, then the action of set P over n minus 0 is free. Then this group satisfies M and N property. Then we can use the results of Wolf and Luke and Jim Davis. Yes, and then we have this isomorphism of set M modules. The cohomology of this group is isomorphic to this tensor product, but the second part, for this part, we can use the Wolf and Luke results. Then we have something like that. The cohomology of M invariant by the action of set P. Direct sum with the cohomology of some conjugacy, some representative of the conjugacy class, of certain conjugacy class. Okay, and taking invariants, we get the following result. The group, the G invariant part of this group cohomology have two parts. The torsion free part, given by the G invariant part of the group, the tensor product of these two cohomologies of free abelian groups, and the P torsion part. Also appears this cohomology of this free torsion, abelian free torsion group, tensor with this part. The sum of the cohomologies of some finite groups corresponding to certain conjugacy classes. Okay. Okay. Now, what is the idea? The idea is try to explain how to compute this part, especially the P torsion part. Okay. How to compute the invariance of this model, the G invariance of this model. G is and to do that, we need the following elementary lemma. Let F be a finite abelian group, and let M be a F module. Assume that M is a finite generated free abelian group. Then M can be decomposed as a direct sum of F modules, each of them with constant isotropy. It means that the M is equal to a direct sum of modules, and if we take an element, a non-zero element in MK, the isotropy group is equal to K. And moreover, this MK is isomorphic as an F module, as to take the fixed point set the fixed point group corresponding to K, and divided by the fixed point set of bigger groups. Okay. The proof is elementary. And how to use that to compute the invariance? The observation is that every finite subgroup of this group is abelian, we have that the action, it implies that the action of G over this module is by permutation. Okay, it's by permutation. It's a G permutation module. Then we could compute the P torsion part in the following way. You could express the module M as a sum of a module of constant isotropy, and we know already that the P is isomorphic to this cohomology group, but M can be decomposed this way. Then we have this isomorphism. It is an isomorphism of G modules. These isomorphisms are isomorphism of G modules. Then we have here this direct sum. In terms of a set of conjugacy classes, we have really this isomorphism. P is isomorphic as a set M set to this Cartesian product, where this P, capital PK, denotes the set of conjugacy classes of maximal finite subgroups of the corresponding part, of the corresponding module of constant isotropy K, semidirect product with set P. On the other hand, we already proved that this PK is the co-kernel of the action. Sorry, here is T minus the identity, restricted to MK. Then we have this implies that we have that the set PK can be decomposed as a union of orbits. One orbit with trivial action, that the orbit corresponding to the group generated by 0, T. Is the conjugacy classes, the conjugacy classes of the group generated by 0, T, and the other ones. The other ones have always constant isotropy K. Then we have this decomposition as G orbits, one orbit with the isotropy G, and the other ones with isotropy K. We can count the number of orbits, this number WK. WK is this number. It is just because we know the size of PK, and we know that as constant isotropy, then we can count the number of orbits. Okay. Okay. If we take then this Cartesian product, we have a decomposition of PK as orbits. Then if you take the Cartesian product, it gives the composition of P as a union of orbits. It can be parameterized by families of subgroups of G in this way, and the number of orbits can be computed, and this number W of capital A is this product. Okay, this number is a number only depending on the decomposition of M in constant isotropy modules. Okay. In a similar way, we can decompose also these other sets that describe the cohomology in any degree beta. In a similar way, with the composition of orbits with certain isotropy groups, and the number of orbits of each type can be computed also with a number only depending on the composition of M in constant isotropy modules. Okay, and the theorem. This is doing work with Luis Jorge Sánchez in Mexico City. The p torsion part of this cohomology group is isomorphic to set p to the x, and this x is this number. Okay, this complicated number is obtained by this part of this first sum is given by the unit formula. Here appears the rank of the cohomology of the free part, and these numbers that appear here in the decomposition on orbits. Okay, let me give just some ideas about the proof. Denote by TP star the p torsion part of the group cohomology. We already proved that the p torsion part is isomorphic to the invariance of this module. But this the module corresponding to the cohomology of the finite groups is because the set is decomposed in orbits, then the module is isomorphic to this module, to this permutation module. Okay, and this part, because this is a permutation module, it implies that this part really is an induced module. It's an induced module from this intersection of the family A to the group G. Then the fixed point of these modules really are isomorphic to the A. Sorry, here is intersection of A. Is the fixed point group of this part of the cohomology of the torsion free part invariant by this intersection. Here is intersection of A. And then you compute the rank over set P of this set, you get this answer. Okay. Okay. More important than the formula, not that the important thing I think is that the number of orbits or the numbers involved here do not depend only depend on the decomposition in constant isotropy modules. Okay, let me say a few words about the free torsion part. We know that the free torsion part is isomorphic to this one, the G invariant part of this tensor product. But to compute the rank of this part, we could take complex coefficients. And in complex coefficients, it is just a G representation. It's a complex representation of the group G. And the invariant part of a complex representation is given just by count how many trivial representations appears in the decomposition. We could compute it, for example, using the orthogonality relations. Okay. Okay. Then it gives a method to compute completely the group cohomology of these groups. And corollary, the torsion part of the group cohomology only depends on the ranks of the composition of this module in modules of a constant isotropy. Okay. Note that may happen that two non-isomorphic groups could have the same or are the ranks the same decomposition module. Then could happen that we have two non-isomorphic groups that have the same cohomology of the same of isomorphic cohomology torsion part. Okay. Okay. Now, let me talk quickly about the Baum-Connes conjecture. The Baum-Connes conjecture predicts that certain map called the assembly map is an isomorphism. The assembly map is defined from this group. This is the gamma equivariant K homology group of the classifying space for proper action, this E bar gamma, and goes to this group K star of C R star of gamma. It is the K theory, the topological K theory of the reduced C star algebra. What is the reduced C star algebra? You could consider the complex group algebra of the group, the complex group algebra of gamma. It is a ring, but you could complete this algebra with certain norm. For example, you could include this the complex algebra inside the as operators in L2. You could complete using this the norm, the L2 norm. Then we get the reduced C star algebra. Okay. And the Baum-Connes conjecture says that this map is an isomorphism. Note that this algebra, for example, see, gamma is non-commutative, non-abelian. This algebra is non-commutative, and then the computation of the K theory of a non-commutative C star algebra is very, very difficult. On the other hand, if we know, for example, if we could decompose E bar gamma as a gamma CW complex, if we have an explicit decomposition, in theory, at least in theory, is possible to compute this side. On the other hand, this side is very, very difficult. Okay. In many cases, for example, these algebras that we get here are irreducible, non-abelian, non-commutative, and irreducible. Then there is no way to use, for example, extension or something like that to compute. Okay. On the other hand, here we could try to decompose and use a spectral sequence or exact sequence to compute. Okay. Okay. What is this K star gamma? It's an equivariant generalized homology theory and could be defined in many ways. Let me say 3 ways to define. For example, you could define it using equivariant K theory groups, defined by Kasparov. The idea of here is that we could consider cycles in K homology in some sense as generalized elliptic operators. Then we could define what is a gamma equivariant generalized elliptic operators and divide it by some relations, and in that way you could define this group equivariant gamma equivariant K homology. The other way to do that, to define this, is using spectra over the orbit category. The definition is given by Luke. And my favorite is using configuration spaces, following, in the non-equivalent case, following ideas of Adem-Gomez-Pan-Petrosyan, and in the case by myself. There are many other models for equivariant K homology. For example, you could define also using the geometric model, using maps to the space X. Let me say. Something you could define using triples. AEMF, where E is a vector bundle over a manifold, and F is a map to space X. And what is K homology of X? Is the equivalent classes of this kind of triples, EMF, divided by certain equivalence relation. Okay, maybe M as CNC manifold. And the relation is defined using, for example, a cobordism, spin C modification, and some other relation. Okay, but okay. There are many ways to define equivalent K homology, but the main property that we need to use is that this K star gamma is an equivariant generalized homology theory. It means that it satisfies the axioms of a generalized homology theory. In particular, it satisfies the Mathbb axiom. Okay. So, by classical results, the Baum-Connes conjecture is true for these groups. It is because the classifying space for proper action is a Hilbert space and the action is isometric. And the classical result of Hickson and Rowe maybe that prove that for spaces with this property, the Baum-Connes conjecture is true. Then we can compute the K theory of the C-star algebra via gamma equivalent homology. Okay, and the theorem is that this K theory group is torsion for these groups. How to prove that? Really, the idea is that Davis and Luke prove that this is true in the case that the number, this M is a prime number and the conjugation action is prime. Okay. Then we know by Davis and Luke theorems, we know that this K theory group is torsion group. Okay. What is the idea to extend this to any action of set M? The idea is, again, prove that the equivariant K homology of E bar gamma with certain coefficients is not the invariant group. In this case, is the co-invariant group. The group of G co-invariants of equivariant K homology, but with this set P. Okay, that is the idea, because we already know that this is torsion. Okay. The proof, in order to compute this, for this proof, gamma is this group, set N, semidirect with set over M. We call that E bar gamma is the classifying space of gamma respect to the family of finite subgroups. And the idea is to construct a model of E bar gamma from a model of E gamma in a similar way as when gamma satisfies M and NM property. In this case, note that this group does not satisfy the N and NM property. The group that satisfies those properties is this one, not that one. Okay. Okay. For this, we use the following result of Luke and Bayer. The theorem is the following. The idea is that try to construct models in a similar way as when the group satisfies the M and NM property. And the idea is following. Let F subset of let F and G two families of subgroups such that F is contained in G, and for every element in the difference, every element in the difference is contained in a unique maximal. This is something like the M property, but it's a M property with respect to these two families. Let mu be a set representative of the conjugacy classes of elements in the difference, and then consider the gamma push out. This gamma push out, note that is similar to the push out in the other case. The difference is that here we have to consider the classifying space not for M. Instead of that, is the classifying space for the normalizer. Here the same, the normalizer and the families. Here the family F, and here the family F together with the family of all subgroups of M. Okay, that is the difference, but the idea is similar. Okay, and the proof is similar also. Then X is a model of the classifying space of the big family G, and then we construct a model of the classifying space for the family G in terms of models of smaller families F, F, and F union the family of subgroups. What is the idea? The idea is we need to pass from the trivial family to the family of finite groups. We cannot do this in only one step because the family of the property don't satisfy the property M. The group don't satisfy the property M. Then we can do is to filter, taking the first family as the trivial family, the last one the family of finite groups, and in the K step, consider the family of subgroups that are have ordered a product of K primes. And 0 primes is the trivial family. F1 is the family of a subgroup of order prime, then 2 primes, T primes, and so on. It is clear, by definition, basically, that any element in the difference is maximum. Then we could apply the above theorem because we have the property that allows to apply this theorem to construct this model of the classifying space for the family Fk in terms of the family Fk minus 1. And oh, sorry, I'm out of time. Okay, let me go quickly. Okay, the idea is that for K0, for K equal to 0, we have to prove that the cohomology of the classifying space is just the coinvariance of the K homology of the classifying space for ZP action, and the idea is the same. Consider the extension and the eraser spectral sequence, and again we get an isomorphism. Note that if we apply this to K theory, we have problems because we need to take a completion in some moment. But in K homology, there are no these kind of problems. Then, okay, and later the inductive step is just given by compute the normalizers. The normalizers are given by set M, semidirect product with the invariant part, and then applying the Mayer-Vietoris axiom to the gamma push out. The idea is that you could take the gamma push out for the group gamma complete, but also for the group given by the group given by the action of set T only. The idea is that you have 2 push outs, one push out for this group and the other one for this group. You have a way to compare these both long exact sequence, the 2 Mayer-Vietoris exact sequence, something like that. We have here the long exact sequence for the group gamma, and the long exact sequence for the group gamma. Sorry, the group gamma P, that is the group with the set P action. You could take co-invariance, and as the order of G is prime to P, then the co-invariance preserve the long exact sequence, and then the phi lemma gives the result by induction. Okay. Okay, then this K theory group is torsion free. Also, we can also apply these ideas to compute, for example, the homology of these quotient spaces, that are the toroidal orbifold quotients. And some questions to finish. For example, what happens if you consider a number that is not 3 of squares, any positive integer? The question is that if you could you consider some coefficient in such way that the Lyndon-Hoschild-Serre spectral sequence collapse? And the other one is this group torsion free. Partial answer for the second question. Langer-Luft proof that it is true if the action of Zm over this set is free. Okay, thank you.